Yeah, like how far can you go based on the single one?
If I have 1, I get a half plane. So here the zeros, they go down, but up here, there's another solution for the next row up there.
But you would get everything below that thing.
Yeah, you get a half plane.
Okay.
And 2 non-parallels is better than just 2 half planes. You actually get everything. Because at each level, once I fix one value, it determines the rest of them. So if I have zeros going up, it forces zeros everywhere. Here's another one. So this delta of x minus y, the z inverse delta of negative y plus x for z. And I'm going to check that I'll write it down well. Inverse minus y plus x, y. Reverse delta x minus z. Okay, so again, I just need to check 2 slices. These are all, well, I should have checked that both of these were annihilated by the same polynomial. There they are. It's going to be x plus y minus z there. X plus y minus z, and here is z minus y and minus x. So they're negatives of each other. And here they're also all annihilated by the same polynomial, x minus y minus z. It's easy to see that this is truncated from below in z, because just non-negative powers this side. So this side better also be. And it is because x minus y and negative y plus x are the same. I'm subtracting them. They're the same as long as this is going to be to a positive power. Then the top will be to a positive power, and that's when they're symmetric. And so both of them are truncated below in z. And if I use that identity, I can shift a couple of them. And I can do exactly the same argument to check the other 2 variables. Z. Use that. So this. This is the vertex Jacobi algebra, Jacobi identity. For the trivial, it's the same one-dimensional vertex algebra. We have verified. I haven't defined what a vertex algebra is, but this turns out to be what it amounts to checking. So it exists because this identity is true. So it's trivial, but this identity is not trivial. Now, every Lie algebra, it should say every Lie algebra. In the beginning, I took an associative algebra, I took commutator, and I showed that it satisfied the Lie algebra Jacobi identity. So I want an analog of the commutator. So I have a vertex commutator. So here we go. Z inverse delta. Inverse delta of x1 minus x0. So all these are formal commuting variables. For x, h sub x, I have to explain a couple things here. I'm defining this, so this is going to define what this means itself. I'll say what these are. That's kind of a mouthful. If you erase the delta functions, though, it looks like a commutator. That would be the commutator, AB minus BA. And now, what do I mean by a sub x? A sub x, oh, I should say there's 3 or 6 algebra people in the room. I'm not using standard notation because I think it'll clutter up the paper a little too much for people that haven't seen it. So a sub x is a series, a sub n next to the n, and z, and a sub n. Endomorphisms. Of some vector space. Okay, so you start with some vector space, and if I just had not a series but just one endomorphism, I didn't have these delta functions, then this would be exactly the algebra Jacobi commutator. And so now we have a parameterized multiplication effect. So for each power of x0, I'm going to multiply one of these guys against one of these guys. And the elements I'm using are not morphisms anymore, they're parameterized endomorphisms. So you are parameterizing all the elements with one parameter. So sometimes we'll talk about this as going from a point to a string or something like that. The parameter moves you along a string. So it's kind of a complicated identity. This just means 2 series multiplied how you would normally multiply. Yeah.
But like, what's to say that multiplication makes sense if it's overall of z, for instance?
When is this well defined?
Yeah.
Yeah. So you have to make sure it's well defined.
Okay.
And that's going to be a big part. How much time do I have? I have 10 minutes. 10 minutes? So hopefully I'll be able to say something on that. But, yeah, so this is the regular multiplication. Make sure it's well defined. Not just these multiplying, but I got to make sure it's well defined multiplied against that. Actually, these alone, it's trivial, because I have 2 different variables. So it's going to be no problem. Because x to the 10, x1 to the 9, there's only one contributing factor. But when I multiply that against this, then it gets tricky, because now I'm repeating my variables. It is not a coincidence that these are in the same order. And so what does this mean? This is a series which satisfies this equation when it exists. So the multiplication is defined as long as I can just stick something in here and make the left and the right-hand sides equal. And so that's how I'm defining this guy. And you can show that this satisfies a Jacobi identity. I think I may not write it up on the board. It looks almost exactly like this. So I think this is already, though, how people... Yeah, I'm going to sign on this, and maybe I won't write it up. But it looks like the Lee algebra Jacobi identity, because we got some delta functions on it. So every term in the Lee algebra Jacobi identity is going to be 3 terms. Each one of them's got its own delta function in the front. And yeah, so there should be a proof that that thing is going to satisfy the Jacobi. It should be an analog of the proof that I gave you earlier. So one proof could run like this. I'm not going to do it, but one proof could run like this. You could check, and you plug it into the Jacobi identity, and you check truncation in 2 of the variables. And it's the same kind of annihilation is going to happen. Those delta functions are all going to be annihilated by the same polynomial. So if I check in two slices, then you do get the full Jacobi identity. So the classical proof, actually they checked 1 slice, and they did a whole bunch of other stuff to get the rest of it. But you can in fact check 2 slices, which is also a little tedious, so I won't write it down. But that's one way of approaching checking. So it does require that everything is well defined always. So as long as everything is well defined, that's going to work. So this guy here, if I want this to be well defined, one way of making sure is that this series, whatever it is, has to be truncated below in powers of x. This is truncated below in powers of x, and when you multiply two Laurent series that are both truncated below in the same power, you can multiply them, like by multiplying two power series. So this is truncated below in x, and so I want this guy to be truncated from below in x. If I want to know what this is, that's also pretty easy. I can take, maybe I should have written it this way, but I showed you the two-term delta function idea. I can take x1 out here and here. That is the same as that. Could have written it that way. Let me bother with that. Put that up there, but that's the event to be proved earlier. And so if I take res x1, that does not appear here. And so it'll just erase this term. It'll take off the constant, the identity from the constant term up here. And so if I take res x1 on this side, it is that. That is what the solution would have to be as long as this is well defined when I plug it in. So I'm going to want this to be truncated from below in powers of 0 to make sure that this is going to be well defined. And that amounts to a high power of x1 minus x times this ordering of a and b minus a high power factor multiple of this times b replaced with a b 0. So I'm going to want this to be true for all of my vectors. I mean, all of these guys. I need to be able to find some k so that I can multiply it and it'll annihilate the commutator. I don't make sure that this thing's well defined. So this gives you a recurrence also on these guys. I have to make sure that a times a is well defined. So this is non-trivial. Let's say you just wanted to search for some solution to this. I'll just start looking at low powers of k. Say k equals 2. K equals 1 is going to be too low. You're not going to be able to get anything interesting here. You'll just get something that commutes. And then you'll get back to this. Or did I erase it? No, you'll get back to this again. It'll be the trivial case. If you did k equals 1, it would force them to commute. And it would be trivial. The interesting case is when k has to be so k equals 1 forces it actually to work for k equals 0. Interesting case is when k is bigger than 0. So I'll do k equals 2, and then k sub x is a sub n, x to the, I'll just do x to the n there, and then a sub y. Again, so there's this for k equals 2, you've got x minus y squared times commutator of a sub n, x to the n, y to the n, sum of that over n, 0. And if you work this out, you're going to get a recurrence on these guys. A sub n is equal to 2 times a sub n minus 1, a sub n plus 1, minus a sub n minus 2, a sub n plus 2. You'll notice this is homogeneous in the indices. These always add up to n plus m, n plus m, n plus 2. because this is homogeneous. So I could just, try to find some solution to this where the commutators say are just numbers. So maybe, these are coming from some big vector space, but maybe the commutator is always some number. And then here's a solution to this, where I label the a sub n. Labels the point nm. So it's homogeneous, so if I'm 0 over here, that's fine. And if it just goes up 1, 2, 3, etc. in one direction, it's a commutator, so it better be symmetric. This satisfies it, right? Because this guy should be twice the previous minus that, so 3 equals 2. 2 times 2 minus 1. Linear. Linear kind of return, certainly, so 4 should be 6 minus 2. And if you did this, there's some nice operators that actually do this. But I'm going to want a sub m, a sub negative m, equal m. So maybe I just make one of them x and the other one x sub m, say, and the other one dx sub m. Commutator of those guys is m, or negative m. Make sure you get it in the right order. And so you do that for every stage. And then if m and negative, if you have a sub m, and these two don't add up to 0, then they're going to be different variables, and so they're going to commute, not going to get 0. So it'll work. And so these operators give you what's called a Heisenberg-Lie algebra. So these define Heisenberg-Lie algebra. They span plus 1. So that spans a Heisenberg-Lie algebra. So if you take the polynomials in x1 running higher, and then you use this operator to find where this is a sub m, that's a sub negative m, then that thing is going to generate, in fact, a vertex algebra. So you take that a operator and it's going to sit inside one. As long as I have one vertex operator, in fact, it always sits inside one. You can show that it will generate. So that's a Heisenberg vertex algebra. But you can search for higher. It's always an easy recurrence. And you'll get something maybe looks like, instead of an m there, I went up to k equals 4, let's get 3. Up to k equals 4 and make the middle 3 zeros. Then this polynomial will work instead of n. You just need an odd polynomial. I need it to be odd because I need it to be symmetric. Negatives down here, positives up here. And this is an odd polynomial. If I complicated things up a little bit here, I was requiring that the commutators were numbers. And maybe I could have the commutators be one of the other elements in that list. And so then I could have I'm going to just use this indexing because I don't want to explain why it would be anything different. So let's say you have this as an operator. But this time I'm going to allow the commutators to be other ones of these. So now I'm going to have L of m equals some function of m and n minus L of some other function. So I require that it be some multiple of one of the other ones on the list. Now again, it's going to be, and let's say I want this to be annihilated by the same thing, 2. It's still going to be homogeneous. So if I want these to just all be the same one, along homogeneous pieces, I'll just make this a function of m plus n. I'll take the simplest one there is, m plus n. And then you could check that if I make that n minus n, it's basically this recurrence here that I had up there. So now, one step back, I choose do the, it's called the width. And if I try to kind of combine that with this guy, if I had an extra term that was a constant, I could add this kind of polynomial on there. Some constant. Just need some one-dimensional space. Again, put a little constant in front. 12. And I'll put a mysterious 12th up there. So now this would be the Virasoro algebra, central charge 1. So you can just start searching in the low powers and solve these recurrences, and you will find this is a Lie algebra. You can check that, and you will find that these give you vertex operators, so they generate vertex algebras. And you can start calculating all sorts of things with them. So I guess I'll stop there.
Thank you very much. John, you have time for questions from Ivan.